delay that we've accumulated. So I'm going to talk about OMA standalone. So we had very nice introduction earlier by Manuel about orthology and paralogy. We've heard that also now for a while. I just want to point out the definition of hierarchical orthologous groups. So if you look at the literature, there's still quite a bit of confusion about the different type of orthologous groups. We've been now trying to push for a number of years the concept of hierarchical orthologous groups, and so this could be defined quite rigorously. And I think we should. I think there's also a space for more contribution at the methodological level that explore the properties of these groups. So they are defined in terms of a taxonomic range of interest. So, for instance, at the tetrapod level here, we have a gene tree with 2 mammalian genes and 1 gene in the frog, and so all of these genes are in one hierarchical orthologous group because they descend from this one ancestral gene. Whereas at the level of the mammals, because they are now already this duplication, we have 2 hogs. Okay, and so now you can see why they are hierarchical, because they, depending on the level you go, they will be made of the union of more specific hogs. And they have nice properties because, for instance, if you're interested in the last common mammal ancestor, the gene content of that ancestor will be made of the combination of all of the hogs. So in a way, it's mapping to some sort of notion of an ancestral gene. And so in OMA, this is our resource. I mean, we had a contribution last year at ISMB about the algorithm, but just as an overview, we start with full genome, and then we do all-by-all comparison. That could be lots of alignment with about 2,000 genomes. It's about 100 trillion alignments. And out of these, we then identify the closest pairs, the orthologs. And then from the pairwise orthologs, it's like a graph-based approach, we then try to build these hogs, which kind of embeds now information about multiple species at the same time. And of course, the big challenge is that we are nowhere near complete, and the number of genome increases really a lot. And so, actually, at some point, we thought, okay, we have to focus rather on like the high-quality genome, which don't really increase so rapidly, and let users run the computation on their own side, for the lesser quality ones. And so we've been developing this OMA standalone package, which I'm trying to advertise here. We have a paper that is almost ready now for submission after a few years. And so it runs in, obviously, because of all of the computational costs of doing pairwise alignments, it can run on some clusters. And so we take a combination of public genomes, including the pre-computed all against all, and some user-based contributed genomes, and then we do all against all. We infer pairwise orthology. We infer OMA groups, which are cliques, actually. So these are the cliques that Manuel was mentioning. These are just a subset of the orthology relationships, but we think these are kind of the useful, for instance, to build trees, species trees, so you could get this as an output. And then you could either specify a reference tree, or you can let OMA try to infer one from these OMA groups. And then we will do this hog inference for you. So then we build all these hierarchical orthologous groups. And then we can also do some gene ontology function propagation. So using the Ortholoop conjecture, I let you, where the user can choose how the decay is in terms of orthology and paralogy, however they like it. So we cater to people on both sides of the debate. Okay, so, and that you could get a result in all of these different things. So for instance, maybe Manuel, you should maybe try to implement your method, just as one extra step here. So we've got code for that. So just to give you an application, so we took a challenging phylogeny, the Lophotrochosian phylogeny, which contains animals as charming as mollusks, annelids, rotifers. So this is a sister group to Ecdydozoa within the protostomes. And this is a recent review. Let's say one region of the animal tree that has been especially difficult to resolve is these Lophotrochozoa. And so people have some idea about what is, there are certainly some topology that are deemed incorrect. There are still some uncertainty. And so we run OMA, and so you cannot see this very well here, but it's in red we have OMA, and here we have the number of groups that have a particular certain number of taxa present. So we have 30 species in this data set, so we have many small groups, and then we have a rapid decay. And some methods that are based on profile HMM, they tend to have bigger groups, but we think sometimes they're a bit too eager to add sequence that might be paralogs. And as a result, if we look then at the trees, so this is a tree that was built using the OMA orthologs. Again, the specifics don't matter so much here, but you can see there's a few nodes that are still unresolved, but that are kind of consistent with the literature. By contrast, if you take some other methods, then you either have some branches that are in disagreement with the literature, or some others also that are unresolved. That's the case for hamster, Bosco, and ortho-MCL. So we think we are doing a good job there. And I just want to say, if you're building hogs, hierarchical orthologous groups, a big problem is how you can then analyze this, visualize this. And so we are developing also some downstream tools. So for instance, some ways of visualizing them on a web browser, selecting some ancestral nodes of interest and seeing, what are all the orthologs and the paralogs. And you could also do that. There's a Python library also to, for instance, then collect all of the species, the duplication and loss events along the tree, and build this type of summaries that we've come to appreciate, but which are quite tedious to do if you don't, have the tools for it. So that's in revision, and the code is available. So I'm going to stop here. You can download the code, and I want to highlight Adrian and Jeremy, and thank you for your attention.
Please, next speaker would coming here. Great, thanks. Quick question while we're switching, perhaps.